I'm going to talk about liberating merges via Apartness and guarded subtyping. I'm Han, and this is a joint work with Xuejing and Bruno. So when we're speaking, what we are trying to do is to develop a calculus that enjoys the merits of both OOP and FP language. We are doing so based on intersection types, and in prior work, we have studied the encoding of basic OOP data structures. So to begin with, let's first talk about intersection types and their calculus. Intersection type, namely, is the intersection of two types, can enjoy the feature of both types. Here is a program example where you use the program variable of intersection type. X is of the type int and bool, which is later passed to the evaluation context successor x and not x. Successor x requires x to be of type int, while not x requires x to be of type bool. Because x is of type int and bool, thus this program can pass type check successfully. So after we get the intersection type, the next natural question to ask is what terms are of intersection type? There are many ways to construct terms of intersection type, and here we follow the line of work of merge operator. Merge operator, denoted by double comma here, can merge arbitrary two terms together. Here, we merge one with true together to get a term of the type int and bool. And if we pass this one merged with true to the program variable above, then we'll get the following result. Successor function requires the parameter to be of type int, therefore successor one merged with true will be finally evaluated to 2. Similarly, not one merged with true will be evaluated to false. What we are interested in this merge operator is that it offers very good compositionality. Whenever we want to compose two objects, even different objects like integers and Boolean, all we need to do is to merge them together with a merge operator. However, merge operator comes at its limitation. That is, it has a non-deterministic semantics. So in 2016, Oliveira proposed the disjoint intersection type to pose disjoint restriction on merge operator to make this calculus deterministic. Disjointness is a relation on two types, suggesting that two types has nothing in common, or we say the common supertype of two types can only be top. And let's see two examples. Here, the first example is one merged with true. One has a type int, while true has a type bool. Since int and bool has nothing in common, therefore these two types are disjoint, and we can merge them safely. However, we are not able to merge one with two because both of the terms have the type int. Their common supertype can be int, which is a non-top type, and this merge has a non-deterministic semantics, where one merged with two can be evaluated to either 1 or 2. These are the basics of the disjoint intersection type and the merge operator. And next is our work. So the problem we found with disjoint intersection type is that it is too restrictive in that some of the useful feature like function overloading is not doable inside the intersection type calculus. Function overloading is one kind of feature that is shared in many programming languages. It is one kind of polymorphism over parameter. It allows you to implement many versions of function for one function. Such as, on the left-hand side, you got a function overloading example in C++, where you got two add functions. One add is for add int, the other add is add double. So in the subsequent program, whenever you want to add two things, you only need to write the function name add and let compiler decide which version or implementation is the correct one to use in the context. And Haskell shares a similar feature of function overloading, and here we demonstrate the example function show. Show is a function will convert everything into a string, and here the type class defines the interface for the showInt and showBool, which converts integers and Boolean into string. What interested us is that this idea of function overloading is very similar to what we have in merge operator. The idea of enjoying many different implementations for one function simultaneously is the idea of we are doing with merge operator. So if we are going to implement the function overloading example in our intersection type calculus, all we need to do is to merge different implementations together, such as on the left-hand side, the C++ example. If we want to implement this, all we need to do is merge the two different implementations of add together. However, we cannot do the example on the right-hand side, and let's see why. Suppose we got a showInt, which converts integer to string, and a showBool, which converts a Boolean to string. If we are trying to merge these two functions together, it gets rejected in the disjoint intersection type because it finds a common supertype of int and bool to string. which is a conflict identified by disjoint intersection type, and we are going to change it. So the next step is to change the conflict resolution inside the intersection type calculus. What we do is to look into the current OOP language design, and we find a feature called delayed conflict resolution, which will be introduced at the next slide. So what we do is to take inspiration from such mechanism, and we also like to provide some insight towards it. And let's talk about conflict resolution. So in disjoint intersection type, the conflicts are identified as non-top common supertype. And in OOPs, conflicts are usually conflicts between data structures and names, such as we got two records here. The first record is x1, y false, and the second record is y true, z true. If we are going to merge these two records together, we identify a conflict in the label y, because both of the records has a label y. And then we have to do the conflict resolution for them. There are basically two categories of conflict resolution, the immediate one or the delayed one. The immediate one requires you to resolve it once you discover it, such as you either resolve it by hand by removing one of the y labels inside one of the records, or you let compiler automatically do the job for you. Most of the programming language and our previous intersection type calculus do an immediate resolution. However, a delayed resolution is also possible, where we don't abort the program once we find the ambiguity. We later abort the program when we use it. And here is a delayed conflict resolution example inside C++. Here, suppose we got two classes. One is the class stack, and the other is the class drawable. Both of the class has a virtual function method called draw. You may find that the draw function have different implementation inside the class. However, when we define a third class called the drawable deck, which inherits these two classes, the C++ accepts it. It will later abort the program when you call the draw method of the drawable deck, but at this stage, the drawable deck is accepted. So the delayed conflict resolution is to delay the conflict resolution, conflicts until you use it. So we take inspiration of it, and what we are trying to do is to delay the conflicts between the function overloading until we use it. And we are going to show this by the example of Xuejing merged with Xuebo. Okay, so this is a diagram of the Xuejing and Xuebo in terms of the subtyping relation, where Xuejing has a type of int to string, while Xuebo has a type of bool to string. The middle gray part is the overlapped part, which is a common supertype of both types. So what disjoint intersection type do is it adopts a very conservative way of dealing with conflict. That is, whenever we find any overlapping between two types, we reject the merge of them. However, in the view of delayed conflict resolution, we can delay such conflicts. We are happy with two terms merged together as long as we have methodologies to tell them apart. So here, in this simple case, in the non-intersection type case, for types like int and bool, we say they are not conflicting as long as they are not subtype of each other. So this is the new conflict notions for our paper, and all we need to do is to generalize these conflicts to the general types like intersection types. For intersection types, they can view as a series of non-intersection type merged together, and we illustrate using the concept of type components. So our apartness, our conflict notion is that we say A is not conflicting with B as long as all of their subparts, subcomponents, or we say the non-intersection types are not subtype of each other. So this is the first notion of our paper, which is apartness, and there are more things to do. So for disjoint intersection types, the disjointness defines the notion of conflicts, and the subtyping is for the safety checking. In our work, we have relaxed the disjointness to apartness. Therefore, we need to strengthen the subtyping to the guarded subtyping. And let's illustrate the guarded subtyping. So here is a type of int to string and bool to string, and some of its supertype. And this diagram, each green arrow denotes a relation of supertype. And you can see the int to string and bool to string has a supertype of int to string, and also has a supertype of int and bool to string. What happens in the disjoint intersection type is that we allow no ambiguity or no overlapping inside any of the type. So whenever we want to cast a type or coerce a type to another type, as long as there's a subtype relation, we are happy with it. However, inside the apart intersection type, it is not the case. The type int and int2string and bool2string may come from some overlapping merges like Xuejing merge with Xuebool. If we are going to coerce the Xuejing merge with Xuebool to the bottom type int and bool2string, then we don't know whether the final terms come from the part int2string or it comes from the part bool2string. Therefore, we strengthen the subtyping to a notion of guarded subtyping. That is, it is a guarded subtyping of B when there exists unique coercion from type A to type B. We replace all of the subtype checking by the guarded subtyping checking inside the type system to gain the determinism of our apart intersection type calculus. So these are the two notions of our paper, and there are some of the other things we provide in our work. The first serial-optical consequence of our apart intersection type is that we are able to have complete conflict resolution. Inside disjoint intersection type, we pose a disjoint restriction so that any types can be merged only when their common supertype is top. This results in some of the conflicts cannot be resolved. However, in our relaxed apartness, all of the conflicts can be resolved, and even better, it can be resolved automatically. Besides, we talk about apartness and guarded subtyping in terms of the language of specification, but to put them into practical usage, we have to develop algorithm for them. We also include that in our paper. Furthermore, we provide source and target calculus, which encode all of our examples, and we show that the soundness of embedding such mechanism into an intersection type calculus. Finally, all of our theorems and lemmas are formalized in rock. And thank you for your attention.
Thank you for the talk. Can you go back one slide, please? Yeah. This looks to me like you do covariant function subtyping, because int to string, is that really a subtype of int and bool to string? That seems wrong comparing with the arrow rule, or I misunderstand something.
Sorry, just the voice is a bit low.
Okay. So if we look at the arrow int to string, is that a subtype of int and bool to string?
Yeah.
But that violates the contravariance rules for functions, so I'm confused.
The error is a supertype relation.
But
the error is the supertype relation. The reverse is the subtype relation.
Yeah. Okay.
So
sorry, I got it the wrong way.
Yeah.
Sorry. Thanks for clearing that up. Thank you.
Any other questions? Yep.
Hi. I noticed with your merge operator, it seems like, or at least with the disjointness version, so maybe the Apartness corrects this, and I'm curious to understand. It seems like if you have more precise information about your expressions, you're more likely to reject the expression.
Yes.
Wouldn't you want more precise information to make it more likely the program is acceptable?
There are two parts of it. If you merge too many things, then it has a stronger possibility to have conflicts between these things. But if you make things more precise, in our case, it is to make a type to be a subtype. In this case, it will have less conflicts. I don't know how to illustrate this. So, such as the example here, you got int to string and bool to string, and if you merge more and more things in the top type, in the topmost type, then it has more possibilities to have conflicts. But if you are going to make things more precise, it is actually going way down here. And if you make one part of the things more precise, it has less possibility of conflicts because you know more about the things, so it has less chance to conflict with the things that is very coarse.
Cool. Thank you.
Thank you.
I had a little question. So do you have unions in your system?
Sorry.
Yes. No, but it's fine. Do you have union types in your system?
No. Actually, we had one version of union type, but it lose it has some conflicts with the distributivity rules in the subtyping for intersection type. And we tried a lot, but we don't know how to fix it. So finally, in our presentation, we only got the intersection type. But it's a worse direction to explore in our future work.
Okay, cool. Thanks. Okay, thanks the speaker again.